Hello and welcome to Lecture 2. Today we are going to talk about disease transmission. A traditional model of infectious disease causation known as the epidemiologic triad is depicted in the figure above. The triad consists of an external agent, a host, and an environment in which host and agents are brought together, causing the disease to occur in the host. A vector or an organism which transmits infection by conveying the pathogen from one host to another without causing disease itself may be part of the infectious process. In the traditional epidemiologic triad model, transmission occurs when the agent leaves its reservoir, that is their natural environment, or host through a portal of exit, is conveyed by a mode of transmission to enter through an appropriate portal of entry. Transmission may be direct contact, host to host, droplets spread from one host to another, or indirect, the transfer of an infectious agent from a reservoir to a susceptible host by suspending air particles, inanimate objects, vehicles or fomites, or animate intermediate vectors. Fomite is an inanimate object that carries the disease. Try to think of a doorknob, for example. Okay, so that's not alive, it's not a vector of disease because it's just an object that can carry bacteria essentially. Or your clothing, money. Money is really dirty. You probably all know that. Now, this is an example here of a direct transmission. So you can see this person's coughing. So through the air, bacteria will spread, okay? And through a portal of entry, they will, infect another individual by breathing those droplets. Here's an example of an indirect transmission. So you can see the flies. Hopefully the picture is clear enough. You can see the flies on the little kid's hands. So essentially the flies will contaminate both the apple and also they might bite the child, and the disease will transmit this way. So there are two types of vectors. A mechanical vector just transports the pathogen to a host. No multiplication or development of the pathogen occurs. A biological vector is a pathogen that is part of its life cycle inside the vector, then it is transmitted to the vertebrate. Biological vectors, on the other side, is a vector in which an organism goes through a part of its life cycle inside the other person. So it replicates. Try to think about mosquito and malaria, okay? Mechanical vector is a vector in which an organism is transported, but the organism does not go through aspects of its life cycle while in contact with its vector. It does not replicate, okay? So try to think now a housefly transporting E. coli. So it's just simply going to touch your meat, for example, and the contamination will occur. Just like an iceberg is underwater and hidden from view, except its tips, disease can exist while exhibiting no symptoms whatsoever. Only clinical illness is readily apparent. That means you can literally look at someone and they would look sick. Either they might be having some kind of a skin disorder that makes them look differently. They might be coughing, tearing, redness, any sign whatsoever that would fall under the clinical illness. Okay, it is when the disease is apparent. The iceberg concept is important because it is important to not only count about clinical apparent cases we see, but also infected people who may not show signs of illness, but yet they are. For example, people who contracted polio infection were not clinically ill at the beginning. Meanwhile, infected individuals can still spread the virus to others. Thus, we can not only understand and explain the spread of polio unless the pool of inapparent cases are recognized. But in the case of non-clinical or subclinical disease, as we said, the disease is not apparent, so it's not visible to the naked eye. So probably you're going to need some kind of a screening or diagnostic test in order to identify that the individual is actually sick, okay? Now, non-clinical disease can be further divided to preclinical disease. So this is a disease that is not yet clinically apparent, but it is destined to become apparent. Number 2 is subclinical disease. So that is disease that is not clinically apparent, but it is not destined to become clinical apparent. Then we have persistent cases of disease, a disease lasting as long as a lifetime. Sometimes infections is treated and they may cause very long-lasting effects. And finally, we have latent disease. So a latent disease is an infection with no active multiplication of the agent. Only the genetic message is present in the host and not the viable organism like a persistent disease. Meanwhile, people who are carriers of latent disease, they can infect others. And that takes us to the carrier's status, okay? So the term carrier is used to describe an individual that is infected by a disease agent and is capable of disseminating that disease agent, but shows no signs of clinical disease. One of the best known examples of asymptomatic carriers was Typhoid Mary. You probably heard of her before. So Mary immigrated to the United States in 1883 and subsequently made her living as a domestic servant, most often as a cook. It is not clear when she became a carrier of the typhoid bacterium, which is a type of Salmonella typhi. However, from the 1900s until 1907, nearly 24 people fell ill with typhoid fever in households where Mary worked. The illness often occurred shortly after Mary began working in each household. But by the time the disease was traced to its source in the household where she had recently been employed, Mary would disappear. 51 original cases of typhoid and 3 deaths were directly attributed to her. Countless more were indirectly attributed to her, although she herself was immune to the typhoid bacillus. Now, the amount of a particular disease that is usually present in a community is referred to as a baseline or endemic levels of disease. The level is not necessarily the desired level, which may be in fact 0, but rather it is an observed level. In the absence of intervention and assuming that the level is not high enough to deplete the pool of susceptible persons, the disease may continue to occur at this level indefinitely. Thus, the baseline level is often regarded as the expected level of the disease. Endemic refers to the constant presence and or unusual presence of disease or infectious agent in a population within a geographic area. Epidemic refers to an increase, often sudden, in the number of cases of disease above what is normally expected in the population in that area. And pandemic refers to an epidemic that has spread over several countries or continents, usually affecting a large number of people. Now we're going to talk about outbreak investigation and occurrence of disease. We're going to read the steps to an outbreak investigation, and I would highly recommend that you go over the particular steps in detail and understand what every step entails. Your very first homework assignment is about an outbreak investigation. And essentially, what's going to happen is I'm going to give you a scenario and you have to figure out what caused the outbreak by following the various steps of an outbreak investigation, okay? Whether infection takes place or not may depend on a whole range of determinants, both intrinsic and extrinsic, which affect the host and the agent. Infectivity is a measure of the ability of a disease agent to establish itself in a host. The term can be qualitatively when an agent is referred to as being low, medium, or high infectivity, or quantitatively. Attempts to quantify infectivity normally involves the use of a statistic known as the infectious dose 50 or ID50. This refers to the individual dose or numbers of the agent required to infect 50% of a specified population of susceptible animals under controlled environmental conditions. The relationship between infection and disease are frequently dynamic in nature. Disease outbreaks caused by the introduction of an agent into a susceptible host population which has not been previously been exposed to that agent normally results in a disease of high pathogenicity, with commensurate severe losses in the host population. When a population is immune to an infectious agent, disease transmission is not an issue. Differences in susceptibility to disease are often seen between different age groups. For example, young children and older adults are more likely to become severely ill from the common flu than young and middle-aged adults. The clinical signs of disease are associated with sexual attributes, as in the case of diseases of the reproductive tract, rather than with the fact that males may be more susceptible than females or vice versa. Can you think of anything else that may affect a disease outbreak? How about extrinsic determinants of disease, such as climate or soil? Climate and soil interact in a variety of ways and affect the environment of the host, the agent, and the intermediate host or vector if they are present. Another major factor is man, who uniquely among animals has the ability to modify both the environment in which he lives and the environment in which he keeps his livestock. Now we're going to talk about herd immunity and incubation period, two very, very important terms in epidemiology. So herd immunity refers to a reduction in the probability of infection of susceptible members of a population when a significant proportion of the individuals are immune. The reduction is observed because the chance of coming in contact with an infected individual is less. In other words, disease transmission is blocked when a critical percentage of the population has been vaccinated. When this occurs, herd immunity levels have been reached. Now, I want you to understand that herd immunity is reached for different diseases at different levels. For example, for some diseases, we may need to immunize 90% of our population, while for other diseases, for example, 80% will do. The concept of herd immunity describes the impact of indirect protection of susceptible members of a population from infection on the protection of the population as a whole. This is brought about by the presence of immune individuals. It is therefore the general aim of those involved in public health to establish herd immunity in the populations for which they are responsible. Vaccinated people act as a firewall that blocks the spread of the disease, slowing or preventing the further transmission of the disease to others. Since the protection offered by vaccines is rarely 100%, the vaccine will become more effective if more people have been vaccinated. This is because the disease may be able to jump from one unvaccinated person to another person who has not been vaccinated, but it's unlikely to jump from one unvaccinated person to one who has been vaccinated. Incubation period refers to a period of subclinical or inapparent pathologic changes following exposure, ending with the onset of symptoms of infectious disease. During the incubation period, individuals are highly infective even though they do not feel any symptoms of the disease themselves. Hence, when the flu virus spreads so easily every single year, it is because by the time most individuals realize they are sick, they are already infected at least another person. The incubation period varies greatly, and some of the factors affecting its duration include individual differences, since not all people are equally susceptible to a virus. Immunocompromised individuals, for example, are more likely to have a shorter incubation period since their immune system will not resist the multiplication of the virus. Thus, they will show symptoms faster. The type of pathogen also determines the incubation period, as well as the dose received at the site of exposure. Airborne diseases are transmitted very easily in comparison with agents that require contact. Isolation and quarantine help protect the public by preventing exposure to people who have or may have a contagious disease. Isolation separates sick people with a contagious disease from people who are not sick. Quarantine separates and restricts the movement of people who were exposed to a contagious disease to see if they become sick. U.S. quarantine stations located at ports of entry and land borders crossings use these public health practices as part of a comprehensive quarantine system that serves to limit introduction of infectious diseases into the United States and to prevent their spread. So what are the questions that epidemiologists need to ask in order to solve disease outbreaks? The very first question is, who was attacked? Okay, the characteristics of the human host are clearly related to the disease: age, sex, race are all factors to consider. The second question is, when did the disease occur? Some diseases have a certain pattern and appear seasonally. For example, diarrheal diseases are more common during the summer months and respiratory diseases during the winter. The third question to ask is, where did the cases arise? Disease is not randomly distributed, thus knowing the location of the outbreak helps us identify the risk factors involved. And now we're going to go ahead and talk about foodborne outbreaks, how we investigate them. So these are the 8 steps that I want you to think. Keep in mind that those are dynamic steps. Sometimes we follow this particular order. Sometimes we spend more time in each step. Okay, so every single case would be a little bit different. So an outbreak is essentially the same thing as an epidemic. It is an increased frequency of a disease above the usual rate, the endemic rate, in a given population or geographic area. The primary reason for conducting outbreak investigation is to identify the source in order to establish control and to institute measures that will prevent future episodes of disease. Whether an outbreak investigation will be conducted may also be influenced by the severity of the disease, the potential for spread, the availability of resources, and sometimes by political considerations or the level of concern among the general public. Most outbreak investigations involve the 8 steps outlined here, and it involves the following actions. Number 1, we need to prepare for the investigation. Before embarking on an outbreak investigation, consider necessary preparations. If the disease is known, research paying particular attention to symptoms, case definition, modes of transmission, diagnostic tests, control measures, etc. The second step would be to verify the diagnosis and presence of an outbreak. We noted that an outbreak is an increase in the frequency of a disease above what is expected in a given population. However, an apparent outbreak can result from either incorrect diagnosis, multiple diseases with similar symptoms, or even changes in record keeping or surveillance practices. It is important to establish that the outbreak is real by examining how the cases were diagnosed and by determining what the baseline rate of disease was previously. For reportable diseases, baseline rates of disease, for example, the usual or expected rate, can be determined from surveillance data, and you can compare rates during the previous month or weeks with the current rates of disease. For non-reportable diseases or conditions, you may be able to find baseline data from state or national vital statistics, from disease registries, or from hospitals' discharge records. Number 3 would be establish a case definition, identify your cases. By a case definition, we mean the standard criteria for recognizing an individual as a case. Establishing a case definition, the criteria that need to be met in order to be considered a case, can be tricky, particularly in the initial phases of the investigation. You want your definition to be specific enough to identify true cases of disease, but you also want it to be broad enough and sensitive enough that it will identify most, if not all, of the cases. As a result, the case definition may change during the investigation. In the earliest stages, it may not be broader and less specific in order to make sure you identify all the potential cases. But later on, it may include more specific clinical or laboratory criteria that will enable you to categorize individuals as probable or confirmed cases. Step 4 would be conduct a descriptive epidemiology. What is that? Descriptive epidemiology focuses on persons, place, and time. The personal characteristic of the cases, changes in disease frequency over time, and differences in disease frequency based on location. Characteristics of person, place, and time are the essential elements of both descriptive epidemiology and for analytic epidemiology. What information will we collect? As far as personal information, you can ask for their name, their address, phone number, age, sex, race, and occupation. Signs and symptoms as appropriate for the type of outbreak. For example, for hepatitis A, one would record the presence or absence of such symptoms such as fever, nausea, vomiting, anorexia, fatigue, etc. laboratory test results. Okay, so probably you're going to look for hepatitis A. You're going to be looking at sources of foods, especially ready to eat or undercooked food and water, raw shellfish consumption, recent travel history, especially to foreign countries, sexual contact. For step 5 and 6, you want to develop and test your hypothesis based on the data you already collected. Step 7 and 8, once you know what caused the outbreak, it is time to prepare the written report to submit to your department and communicate the findings with the people in charge of policy development. So how do we calculate attack rate in foodborne outbreak? Okay, we use attack rates to calculate the risk of disease in groups of people with different exposures. For example, it is common in communal picnics for people to become sick. During a picnic, many food items will be served, and not all people will, eat the same foods or the same amount. So how do we solve a foodborne outbreak? We divide the number of people who ate the food and became ill to the total number of people who ate the food, and may or may not became ill. So essentially, try to think of it as the numerator would be A, and then that would be, people who ate the food and became ill, and the denominator would be all people who ate the food, regardless if they became sick or not. So that would be A plus B, okay? And of course, since it's a rate, we're gonna have to multiply with 100. Let's do an example. So here you have the streptococcal disease in Florida jail. You have 325 out of 690 inmates got pharyngitis. Many reported sore throat between August 16th and the 22nd. Officials suspected a foodborne outbreak. And this is a table showing the items consumed and not consumed by what percent of the population. If we use the formula for attack rates, we can calculate an attack rate for every single food item. So here we have beverage, we have dessert, we have egg salad, and carrot sticks. Okay, so you can see here, if I may go with my mouse, you have the number of sick people. So these are people who actually ate those foods and people who did not eat the foods, right? So 179 people here drank the beverage, okay? And it seems like 149 of those who drank beverage became sick. 22 people did not drink any beverage, and these are sick as well, okay? Now, dessert, you have 60 people who ate the dessert, okay, and became sick. And you have 4 people who did not eat dessert, yet they still became sick. Egg salad, you have 176 people who ate the egg salad and became sick, and you have 27 people who did not eat the egg salad and become sick, okay? And finally, carrot sticks. As you can see, there's only 12 people here that ate the carrot sticks and became sick, and 0 people who became sick and ate carrot sticks. Now, as you can imagine, there's a lot of overlap, right? So usually people, when they go to a picnic or they're eating in an open buffet, they're not going to just have a beverage. They're usually going to get a little bit of the carrot sticks, a little bit of the egg salad, a little bit of the dessert. They're going to drink the beverage. So the question is, out of all these, given that you interview those individuals, which is what caused the disease? Was it the beverage? Was it the dessert? Or was it the egg salad? So by knowing what everybody, hopefully they were recalling the information correctly, because that is another thing. Recall is a huge issue. Remembering exactly how much you ate of what. Okay, and then you making this nice pretty table and then calculating the attack rates to figure out what actually caused the outbreak. So here, for example, you can see we calculated the attack rate for those who drank the beverage, and we can see that, for example, if you take 179, that would be the people who became sick, over 264, these are the total people who actually drank the beverage, right? So that would be your attack rate times 100, that gives you 67.8%. Okay, you would do this for every single food item, and you would calculate the attack rate. So apparently here you can see that you have 67.8% of people who drank the beverage, okay, and 77.9% who ate the egg salad became, I guess that attack rate is very high in comparison with the attack rates that we see for people who did not eat. Right? If we have to compare beverage and egg salad, I can guarantee you that the majority of people who ate the egg salad, they also had a drink. So most likely the culprit here would be the egg salad. Okay? And that is all for today. Have a wonderful day, and I will talk to you next week. Bye-bye.